Hello everyone. Today we are going to talk about chapter 5. Firstly, I'm going to tell you guys the chi-square chart and tables. As we all know, in the last two chapters, we have learned t-chart and z-chart. But in this chapter, we have a new one, which is called chi-square chart. So this section consists with more than two population. There are two ways to solve the multinomial experiments, using one-way table and contingency table. And I think it's still the key points to compare the numbers that's calculated and the number showed on the table. And here's the formula. X squared equals to the O minus E squared divided by E and sum them up. So firstly, I'm going to show you guys what is one-way table. So first the step for solve the one-way table question is still making the HO and the HA. So the HO for the one-way table is probabilities are equal to the clump, and the HA is at least one of the multinomial probabilities does not equal its hypothesis value. And the step 2 is test the statistics. So as we can see the formula as I said before, and here's the formula. And E is equals to the expected value, O represents the observed value. And here's a very important formula for you guys. E equals to NP. N represents the whole sample size, and P means the percentage. So that's the E equals to NP. And here is the table for the chi-square chart. And as you can see, there are 30 different kind of degrees of freedom and 8 different areas shows in this chart. And one important thing I want to mention to you guys is do not add or minus anything in the area because it's from the right of the critical value, which means you don't need to do any change when you get the alpha. And when I first time do the solve the questions, when I get the alpha value was 0.05, I was trying to minus it, so I get 0.95, and then I found a value from like 6 and 0.95, so I get 1.635, but actually value is 12.592. Step 3 is that I mentioned before. The x chi-square from table alpha is always to the right. Compare x chi-square from the calculated with x chi-square in the table. So the degrees of freedom is k minus 1. K represents the possible outcomes, and alpha should be given by the question. If not, use 0.05. Finally, step 4, conclude, is to reject the null or fail to reject the null. And here's an example from our notes, and we are going to practice right now. 1,000 students were randomly selected from San Jose State University, and it was expected that 25% of the students were freshmen, 20% are sophomores, and 35% are juniors, and also 20% seniors. The follow table shows the observed values, and as we can see, it's the observed values. So how can we solve this problem? And the first step we're going to do is to calculate expected value. As we can see in the problem, there are 25% of students were freshmen. N is 1,000. According to the formula, we have E equals NP. It's 1,000 times 25% equals 250. And also 20 sophomores, which means 200. And 35% means 350, and the last 20% means 200. And we can see the expected value, observed value, and also the E minus O squared, and also the E minus O squared divided by E. Here's all the value we got on the table. So next step is, if we got this table, the problem may be solved very easily. We can see the formula here, and we can do the xcal. So how does xcal equals to 8.096 comes from? We can see all this value on here, e minus o squared divided by e, and we just need to sum it up. So that equals 4.9 plus 0.5 plus 2.571 plus 0.125. That's made the answer. And then we know the HO is percentage 1 is 25%, percentage 2 is 20%, percentage 3 is 35%, and percentage 4 is 20%. And the HO is at least 1 is not equal. And now, according to the table, we can get the x chi from the table. The degrees of freedom should be k minus 1, which 4 minus 1 equals 3. And alpha value didn't given, so we use 0.05 now. And degrees of freedom should be used 3, and alpha should be 0.05, and we got number 7.81. And we can see the xcal value is 8.096, which bigger than the x table value, which we got a conclusion. We reject the null hypothesis. Now we are going to move to contingency table. The multinomial experiments are such that the data are classified according to two criteria. Classification with respect to two factors. Two-way table or contingency table presents multinomial data classified on two scales of classification. And now we can see the formula of the expected value here. It's row total times column total divided by total sample size. And that I need to mention is DF. The degrees of freedom here is R minus 1 times C minus 1. So here's the steps how to solve the contingency table. First step is to make the HO and the HA. So if the HO is if something is independent of something, then the HA is something if something is dependent of something. And step 2, calculate xcal and find the x table. And then compare with each other. And the last step is conclude. So which means the same steps from the one-way table. And now here's the little example I need to show you guys from the notes as well. And as we can see on this table, we got Pepsi Cola, Coca-Cola, 7-Up, and root beer. And also 3 kind of different cups, small, medium, large, that people want to drink. And according to research that Pepsi Cola small, there's 150 people drink. Coca-Cola of small people drink like 155. 7-Up is 151. Root beer become 155. And Pepsi Cola's medium drinker, there are 200 people. Coca-Cola, there are 205. 7-Up, 195. Root beer, 190. And for the large drinker, the Pepsi Cola is become to 100. And Coca-Cola 110, 7-Up 105, root beer becomes 95. So what's our first step to solve this problem? Absolutely, to calculate the total. And also the expected value shows here is row total times the column total divided by total sample size. That I need to review again. Now we see this table. For the total value of the Pepsi Cola is 450. For the Coca-Cola is 470. And 7-Up is 454. And root beer is 440. And the total sample size of the small cup value is 611. Medium is 793. And the large is 410. And the most important part, the total sample size is 1,814. Then we need to explain how we come this small blue number besides to this black number. How this 151.6 and 158.3 comes from. It's from the value we introduced before. Expected value is the row total times to the column total divided by total sample size. And Then we can see expected value. Now this blue number comes from like small Pepsi Cola is 450 times 611 divided by 1814, which comes from 151 and 6.6. So that's all this value comes from. That the total rule number times total clone number divided by total sample size. And now the steps for solve this problem is HO, I've made the HO and HA. Now for this question, HO is if the size of soda is independent of the type of soda. And the HA is if the size of soda is dependent of the type of soda. In step 2, calculate at xcal and find xcal on the table. I mean x on the table. Also for the step 3, compare with each other, find which one's bigger, which one's small, and the last step is conclude. And now we got all these values. It's time to solve the problem. Firstly, we still need this formula, xcal. Xcal equals to O minus E squared divided by E and sum them up. And how to do the xcal here? We need to add all these xcal one by one. So solve the first xcal as 151 plus 6, which is expected value, minus 150, which is observed value, and square them. Divided by the expected value is 151.6, and get the answer. Do that one by one, and add them all up, get the 1.09. And then we need to get the degree of freedom. Degree of freedom here is there are 3 different cup size, small, medium, and large. So as 3 minus 1 get 2. And 4 different kind of type drinks, Pepsi Cola, Coca-Cola, 7-Up, and real beer, which is 4 minus E equals 3. And 2 times 3 we get 6. So the degree of freedom is 6, which help us to get the value of the x table. So we can see the chi-square here. The x table degree of freedom is 6 here, and we get the alpha value is 0.05, which is normal value is 12.592. That's the that's the x table. Then we back to the question. We can see the value is 12.592, and then we get a table which shows 1.09 is much lesser than the 12.592. So which means there's not enough data to reject the null hypothesis, which means fail to reject. And also, here's a little tips for you guys. When you calculate all these values, try to calculate the largest one, and then compare to the compare for the x table. You don't have to calculate all of them. You just need to maybe calculate 1, 2, 3, the largest number that you found, and get the large number. If it's over than the x table, then it's reject. So if you didn't find the largest table, add them up, it's more than the x table value. You may need to try to do it one by one, and sum them all up. Try to compare with the data showed on the table. So, and that's all for me. And next, we are going to talk about best fitted line.
So I'm here to talk about formulas for the least squares estimates. So best fitted line. Best fitted line is a line that goes through all points from relation of 2 correlated variables such that the sum of squares of error is the least. So some equations to solve problems. Equation of best fitted line is y hat equals mx bar plus b. And slope, which is m, equals ssxy over ssxx. and y-intercept b equals y bar minus m times x bar. SSXY equals the sum of x minus x bar times y minus y bar. SSXX equals the summation of x minus x bar squared. So let's take a look at an example. Find the best fitted line for the following points: 1, 2, 2, 2, 3, 4, and 4, 4. So first, plot in x. So it's 1, 2, 3, and 4. And then plot in y, which is 2, 2, 4, 4. And then calculate x bar, which is 2.5, and y bar, which is 3. Next, calculate x minus x bar, which comes out to be negative 1.5, negative 0.5, 0.5, and 1.5. Then calculate y minus y bar, which is negative 1, negative 1, 1, and 1. Then calculate the square of x minus x bar, which comes out to be 2.25, 0.25, 0.25, and 2.25. Last but not least, calculate x minus x bar multiplied with y minus y bar, and it comes out to be 1.5, 0.5, 0.5, and 1.5. In order to find the best fit line, we need to find the slope, which is SSXY over SSXX. In this case, the SSXX is 5 and SSXY is 4. So m equals 4 over 5, which is 0.8. Then we find the y-intercept b, which comes out to be 3 minus 0.8 multiplied with 2.5, which equals to 1. So the equation of the line is y hat equals 0.8x plus 1. So take a look at practice question. Find the best fitted line for the points 20, 30, 25, 26, 27, 18, 12, 6. So step 1, as talked before, plot in x and y values. So 20, 25, 27, and 12 for x. And the corresponding y is 30, 26, 18, and 6. Calculate x bar and y bar, which is 21 and 20. And the x minus x bar is negative 1, 4, 6, and negative 9. And the y minus y bar is 10, 6, negative 2, and negative 14. And the square of x minus x bar is 1, 16, 38, 6, and 81. And the x minus x bar multiplied with y minus y bar is negative 10, 24, negative 12, and 126. Step 2. SSXY equals to the summation of x minus x bar times y minus y bar, which equals 128 in this case. And the SSXX is the summation of x minus x bar squared and comes out to be 134. So the slope is 0.955. Then we calculate the y-intercept b, which equals to negative 0.055. Step 3. So after we find out that the equation of the line should be obvious, which equals to y hat equals 0.955 x bar minus 0.055. So another practice question, but this time we're gonna find the best fitted line using a calculator. Find the best fitted line for the following points: 1, 1, 2, 1, 3, 2, 4, 2, and 5, 4. Step 1. Plot in x and y. So x is 1, 2, 3, 4, and 5. and y and corresponding y is 1, 1, 2, 2, and 4. Step 2. Use your calculator, go to Stat, Edit, and then plug in x value into L1 and y value into L2. After that, press Stat again and go to Tests. And under Test, go to option number F, LinReg t-test. Press Enter. X list should be L1 and Y list should be L2. Then hit Calculate. Step 3. And this time, the calculator should already give you the formula of y equals ax plus b. And a should be negative 0.1 and b is 0.7. So the solution is y hat equals 0.7x minus 0.1. So another question. Question A. What would your expectation for a value of y correspond to x equals 1.5? So given equation of the line y hat equals 0.7x minus 0.1, plug in 1.5 for x, calculate for y. And question B. How much error would one get if find y for x equals 2? Given equation of the line again, y hat equals 0.7x minus 0.1. Plug in 2 for x. So y hat equals 0.7 times 2 minus 0.1, which equals 1.3. The actual value of y when x is 2 is 1, which is listed in step 1. When x is 2, y is 1. Next, we have to find the percentage of error. The percentage of error is the absolute value of actual value minus the experimental value all over the actual value times 100%. So in this case, it's 1.3 minus 1 absolute value over 1 times 100%. And this gives you 30% error percentage. So this is everything about the best fitted line, and next we're going to talk about correlation.
Last but not least, this part, my part, deals with correlation. A correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. These are the words that can be found in Chapter 5 notes that Mr. Mosh gave us. In other words, correlation is a statistical technique that can show whether and how strongly pairs of variables are related. Few examples of correlation would be correlation between height and weight, how taller people are heavier than shorter people, correlation between sleep and health, how people who sleep more are healthier than those who sleep less, correlation between glasses and grades, how people who wear glasses have better grades than those who don't. Correlation is to see if there is relationship between two variables. We are not to say if the examples are true or false. To measure correlation, we have to use something called linear correlation coefficient. The linear correlation coefficient, R, measures the strength of the linear correlation between the paired quantitative x and y in the sample. This is also the words from Chapter 5 notes that Mr. Mosh gave us. Few characteristics of the R would be that R is always measured between -1 and +1. When r is closer to 0 or equals to 0, it says that there is no relationship between two variables. When r is positive, as one variable gets larger, the other does too. They move in the same direction. When r is negative, as one variable gets larger, the other gets smaller. They move in different directions. This is also called the inverse correlation. Also, when r is closer to 1 or negative 1, it means that the variables have strong correlation. Same when the r is closer to 0, it means that they have weak correlation. Coefficient of determination is simply correlation coefficient squared. R to the square of the coefficient is percentage of the variation in one variable that is related to the variation in the other. When r is 0.5, coefficient of determination will be 25%, which is r squared 0.25. It means that 25% of the variation is related. When r is 0.6, 36% of the variation will be related. When r is 0.7, 49% of the variation is related. R table and testing claim. The R table shown above looks a little bit different from the R table that Mr. Mosh gave us. The R table that Mr. Mosh gave us doesn't include degrees of freedom. It uses just a plain R, a plain N. Degrees of freedom for R table is N minus 2. So if you add up these degrees of freedom with 2, it'll be the same table that Mr. Mosh gave us. Let's take an example to draw a graph for R table. The graph for R looks like this. When using N as 4, the degrees of freedom would be 2, and when using A as 0.05, looking at the second row, we can see that R is 0.950. For the R graph, you'll have to draw a point in both positive and negative side for R. So looking at the graph, there is 0.950 and negative 0.950. To test the claim for the correlation, the hypothesis would be that there is no correlation, and our claim would be that there is correlation. Using the same example, when N is 4, degrees of freedom 2, and A is 0.05, and when using some examples, when we have a calculation that R equals to 0.5950, same as the R from the table, we can say that there is enough data to reject the hypothesis and say that there is good correlation between two variables. The formula to calculate an R is this. R equals to N times sum of xy minus sum of x times sum of y over radical N times sum of x squared minus sum of x altogether squared multiplied with radical N sum of y squared minus sum of y altogether squared. Using the same example from the previous slide, where N is 4 and sum of x 20, sum of y 30, sum of x squared 110, sum of y squared 236, lastly sum of xy 16. When you insert these numbers into the formula above, you get an R which equals to 0.95. This is an example that I used in the previous slide. Let's do a practice question. Use A as 0.05 significance level to test the claim that the outcomes are not equally likely and the die is a loaded die. This is the table which was given. The numbers, which is 1 through 6, will be our x, and the frequency level, which is 27 to 32, will be our y. To use the formula from the previous slide, it is much easier when you make a table which looks like this. Using the x and y given from above table, we can calculate x squared, y squared, and xy. Since x is 1, x squared will be 1. Since y is 27, y squared will be 727. Using this number, we can see that xy is 27. From the calculation, when you add them up, the sum of x will be 21, sum of y 210, sum of x squared 91, sum of y squared 7522, lastly sum of xy 757. When we draw a graph with degrees of freedom of 4 because n is 6, and using a as a 0.05 significance level, the graph we'll have to draw would look like this. Since the r from the table is 0.707, we mark them in the both positive and negative side. Using the formula and inserting all this sum of x, sum of y, sum of x squared, sum of y squared, sum of xy into the formula, we'll get that r is equals to 132 over 329.23, which is 0.40093, and so on. And because 0.40093 is actually smaller than 0.707, there is not enough data to say it's correlated. It means that we have failed to reject. Another formula to calculate an R would be R equals to sum of zx zy over n minus 1. The z used here is the one we learned from chapter 3. Zx equals to x minus x bar over sx. To give an example, same as the previous formula, to calculate an R, we'll have to draw a table which looks like this, quite similar. Where x and y will be given, we'll have to calculate zx, zy ourselves and multiply them together to derive zx and zy. This table actually looks a little bit more simpler than the table used for previous formula. It would be because it deals with relatively smaller number since x is not squared, but take an account to stuff that we'll have to calculate with x bar and sx using the calculator. It's actually a little bit more complicated than the previous formula. Using the same graph that we used, where zx, zy from the table is 2.87, r will be 2.87 over n minus 1, which is 3, which equals to 0.96. It says that there is enough data to say that there is good correlation between two variables. Let's do a practice quiz. This is the table which you can get from our chapter 5 notes, practice number 2. X is an exam score and Y is an hour study. Looking at the first row, a particular student studied 3 hours to get an exam score of 60. Since n is 12, degrees of freedom will be 10, and using a as 0.05, we'll have to draw a graph which looks like this and points out 0.576. This is the R that you can get from our table using degrees of freedom of 10 and a of 0.05. Using calculator with data, you can derive these numbers of x bar as x, y bar, and sy. Using these numbers, you will have to calculate zx, zy, which is all calculated in table. Looking at the middle of table, you can see that there is a 0 for zy and zx, zy. This is because y equals to y bar, and thus zy would be 0, and all the calculation, including multiplying with zy, which is zx, zy, would be 0. From this table, adding them up of zx, zy, the sum of zx, zy is 6.95. So, using the formula, r is 6.95 over n minus 1, which is 11. Thus, r is 0.63. And since 0.63 is bigger than 0.576, there is enough data to conclude that there is good correlation between two variables. This is all for the correlation part. Thank you.